Greetings, welcome to this new video about Thevenin's theorem. In this video, I will demonstrate the application of Thevenin's theorem through a step-by-step example explanation. By following along carefully, you will gain a clear understanding of how to apply Thevenin's theorem to solve practical problems. Let's dive in and begin with solve the problem number 4. Let's consider this network consisting of 5 resistors labeled R1 through R5 as well as 3 independent sources VA, VB, and IS. The question now is to find the Thevenin's equivalent with respect to terminals A and B. Let's move on to the solution by applying the Thevenin theorem between terminals A and B. We can replace this circuit with a voltage source in series with a resistor, which will be denoted as VTH and RTH. I will start first with the determination of the Thevenin's resistance. This step can be done by removing all independent sources in the circuit, which means the voltage sources will be replaced by a short circuit and the current sources will be replaced by an open circuit. The Thevenin resistance represents the equivalent resistance between terminal A and B. I will consider RA is the series combination of R1 and R5, which is given by R1 plus R5 we get 20 ohms. And I will consider RB is the parallel combination of R3 and R4 is equal to R3 times R4 over R3 plus R4, and we get 10 ohms. Now RTH is equal to the series combination of RB and R2 connected in parallel with RA, which gives by this formula RA times RB plus R2 over RA plus RB plus R2, and we get RTH is equal to 10 ohms. After finishing the determination of the Thevenin resistance, we proceed to calculate the Thevenin voltage. The Thevenin voltage is basically the open circuit voltage calculated between terminals A and B. To find the open circuit voltage VOC, I will apply the nodal analysis method. But first I will consider I1 is the current through the resistor R1, I2 is the current through the resistor R2, I3 is the current through the resistor R3, I4 is the current through the resistor R4, and I5 is the current through the resistor R5. By applying Kirchhoff's current law at node 1, we can write I1 plus I2 is equal to 0. And according to Ohm's law, I1 is equal to V1 minus VA over R1, and I2 is equal to V1 minus V2 over R2. And if we replace the resistors with their numerical values and the voltage VA with its numerical value, and we continue simplifying this equation, we obtain 2 times V1 minus V2 minus 30 is equal to 0. Now by applying Kirchhoff's current law at node 2, we can write I2 plus IS minus I3 minus I4 is equal to 0. And according to Ohm's law, I2 is equal to V1 minus V2 over R2, and I3 is V2 minus V3 over R3, and I4 is V2 minus V3 plus VB over R4. And if we replace the resistors and the voltage with their numerical values, and we continue simplifying this equation, we obtain 2 times V1 minus 4 times V2 plus 2 times V3 plus 80 is equal to 0. Now by applying Kirchhoff's current law at node 3, we can write I3 plus I4 minus I5 is equal to 0. And according to Ohm's law, I3 is V2 minus V3 over R3, I4 is V2 minus V3 plus VB over R4, and I5 is V3 over R5. And if we replace the resistors and the voltage with their numerical values, we obtain 2 times V2 minus 4 times V3 plus 20 is equal to 0. Now from equation 1, we can write V1 in terms of V2. That means V1 is equal to 0.5 times V2 plus 15. And from equation 3, we can write V3 in terms of V2. That means V3 is equal to 0.5 times V2 plus 5. And now by substituting A and B in 2, we derive one equation in terms of V2. And if we continue simplifying this equation, we obtain negative 2 V2 plus 120 is equal to 0. That means V2 is equal to 100 over 2 is equal to 60 volt. And from equation A, we have V1 is equal to 0.5 V2 plus 15. If we replace V2 with its numerical value, we obtain V1 is equal to 45 volt. And from equation B, we have V3 is equal to 0.5 V2 plus 5. If we replace V2 here, we get V3 is equal to 35 volt. VOC is equal to VA minus VB is equal to VA is equal to V1 and VB is equal to V3. That means VOC is equal to V1 minus V3 is equal to 45 minus 35, we get 10 volt. That means VTH is equal to 10 volt. So this circuit can be simplified with respect to terminals A and B with a 10 volt voltage source in series with a 10 ohms resistor. After completing the calculations, I perform a simulation using SPICE to verify our results. Now let's proceed to the SPICE environment. Our network consisting of resistors R1, R2, R3, R4, and R5, an independent current source IS, and an independent voltage sources VA and VB has been drawn in SPICE simulator. Next, I will connect a load to both the original circuit and the equivalent Thevenin circuit and simulate their behavior. Let's move on to analysis, DC analysis, calculate nodal voltages. We can see here that the voltage across the load is equal to 909.09 millivolt in the equivalent Thevenin circuit and is equal to 909.09 millivolt in the original circuit. Is exactly the same. Upon simulation, we can observe that the two circuits have identical behavior when we connect a load between terminals A and B. This outcome confirms the accuracy of our calculations. Alright, thank you for watching this video. If you have any question, do not hesitate to contact me by email or leave a comment under this video and I will answer you as soon as possible. If you like this video, don't forget to subscribe and share. See you next time in another example about Thevenin's theorem. Take care and bye bye.